गर त। ऊ त्यो हेर ऊ त्यो। अँ। अँ भयो 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 भयो। अलिकति ऊ गर त, सिधा गर त्यसलाई।
Should we start?
Yes, I think so. We can start. Since our resource person is already with us, so we can start.
Yeah.
Hello, everyone. Am I audible?
Yeah, good
Yes,
evening.
sir.
Am I
Good
audible?
Yes.
Okay.
Good evening, sir,
Okay.
and good evening to all participants.
Good evening. I'll just start the session.
Yes, please.
So, yeah, good evening, everyone. Very warm welcome to our fifth day of Atal AICTE sponsored 6-day faculty development program on seismic vulnerability assessment, organized by the Department of Civil Engineering, Royal School of Engineering and Technology, the Assam Royal Global University. We are delighted again to continue this academic journey with a highly accomplished speaker who bring with him immense expertise and experience. Our first technical session today is to be delivered by Mr. Binay Karna. Mr. Binay Karna, a structural engineer and doctoral researcher at the Asian Institute of Technology, Thailand, specializing in resilient infrastructure and earthquake engineering. With over 8 years of experience, he has played a pivotal role in post disaster reconstruction, including contributing to rebuilding efforts after the 2015 Nepal earthquake and leading the rapid visual assessment of more than 3,000 earthquake damaged structures in Myanmar. His work combines advanced structural engineering research, such as developing sustainable high performance concrete, with hands on disaster risk reduction and community based resilience initiatives. Mr. Karna has also collaborated on international projects funded by DFID, the World Bank, and the Australian government, and has shared his expertise at global platforms such as UNFCCC, COP29, and the CSI Structural Engineering Conference. Today, he brings invaluable insights on earthquake impacts and resilient reconstruction to the engineering community. We are honored to have you with us, sir, and I warmly welcome you to and hand over the session to you.
Thank you, ma'am. Thank you for your wonderful introduction. So, without much delay, I'd like to dive into our presentation session. So today we are going to present about insights from 2025 Myanmar earthquake and their implications for Northeast India. So initially I submitted the topic for insights from 2025 Myanmar earthquake, but later I thought that implications to Northeast India might be more relatable and more like interesting for the people, for our audience. So moving forward, so let me give you a brief overview about the Myanmar earthquake. So it happened on 28th March 2025 on 6.20 main shock happened. It was the magnitude recorded by USGS was 7.7 and the location was Mandalay, Myanmar. And again, a big aftershock came of 6.7 to 12 minutes after the main shock, whose magnitude was recorded to be 6.7, and the location was Sakai, Myanmar, and the depth was 10 kilometer. And number of casualties were 33,000 plus death and 5,100 plus injuries. So I have kept it in red for purposefully because these data are updating over the time. So you can see that this is the fault line. This is the fault line, and you can see the MMI distribution of Myanmar Mandalay earthquake M7.7. So overview of Myanmar earthquake. It was a super strike slip event of unprecedented scale, and it was of 7.7, and some agencies were reporting it to be 7.9. So I have kept the range from 7.7 to 7.9. But for your information, USGS has identified it as the 7.7 magnitude earthquake, and it struck Myanmar near Mandalay in the Sakai region, making it country's strongest earthquake after 1912. And fault and rupture, the quake ruptured about 500 kilometers of the Sakai fault over 80 seconds, which is huge, and the slip exceeded 3 to 6 meters in many areas, and rupture propagated at super shear speed, faster than shear waves. So, and the intensity, the peak ground acceleration surpassed 1 g with Naypyidaw station, which is the capital city, and they have a better station on that place. So the vertical motion was recorded to be 1.06 G, and this corresponding to MMI X, which is considered as the extreme by the seismic community. And shaking was felt as far as Imphal, which was MMI 5 for Imphal, because I wanted to relate it to our Northeast engineer audience. And talking about the global significance, the event was the deadliest in Myanmar's modern history and the most destructive global earthquake after 2023 Turkey-Syria disaster. It revealed new behavior of strike-slip faults, challenging questions to existing seismic models. This is the tectonic map of active faults of Southeast Asia. This on the right side, you can see the earthquake which happened from 1905 to 2014. These are the recorded earthquakes which happened in the period of about 110 years. So going to the details, so I'll talk about the detail of the tectonic plates. So tectonic setting about the Sakai fault and the plate boundaries. Sorry, I think there's a technical glitch. Okay, so Myanmar earthquake causes. So Myanmar lies at the intersection of Indian, Eurasian, Sunda and Burma plates. Sunda and Burma are the microplates. Just give me a sec. I think there is a technical glitch. Okay. So, sorry for the glitch. So Myanmar lies between the two big tectonic plates, which are Indian plate and Eurasian plate. So which are subducting in each other every year. So, and also Myanmar lies, you can see on the right bottom that there are two microplates, which are Burma microplate and Sunda microplate. So Myanmar lies at the intersection of these two big plates and two minor microplates. So Indian plate converges northwards toward Eurasian plate while sliding eastwards past the Burma plate, creating a highly complex tectonic regime. So you can see that Indian plate subducts towards Eurasian plate, and also it subducts towards Burma microplate, let's say, in eastward direction. So Sakai fault. So this is the plate tectonic. So Sakai fault. So it is a 1400 kilometer long right lateral transformational fault. The Sakai fault accommodates motion between Burma and Sunda plates, and it slips 18 to 49 millimeter per year and passes through major population centers such as Mandalay, Naypyidaw and Yangon of Myanmar. And when we talk about the regional tectonics, the Indo-Burma range to the west and the Sunda megathrust to the south flank Myanmar. These boundaries link directly to Northeast India's fault systems, making seismic hazards transnational. So what are the engineering implications of this tectonic setting? So because of the Sakai fault, effectively a north continuation of Indo-Burma boundary, its seismic behavior holds direct implication to Northeast India. So structural safety in Northeast India cannot be decoupled from Myanmar's tectonic activity. So what I am trying to bring in here is Northeast India can be directly affected by the Sakai fault and the tectonic activity of Myanmar. So now talking about the earthquake mechanics, rupture and super shear propagation. So rupture length and slip for the 2025 quake, rupture was around 500 kilometer of Sakai fault, producing displacement of 3 to 6 meter at surface and up to 7.4 meter at depth. This exceeded prior assumption of the fault's rupture capacity. So it exceeded like more than 30% of the rupture capacity. You can see the photos. You can see the photos on the right, which is taken from a research recently published by Zhu et al. So you can see that the ruptures are like 3.72 meter on vertical. So it was a super shear propagation condition. So for much of its rupture, the fault propagated faster than the shear waves. So super shear is a condition where when the rupture plane propagates faster than the shear waves, faster than the ground velocity. So it's a rare phenomenon. It's a very rare phenomenon, and super rupture amplifies ground motion, creating unusual and intense shaking at distances. And energy releases. The seismic activity release far exceeded the historical slip deficit. So showing that large fault can break beyond expected limits. So it was a kind of very surprising for seismic experts because it exceeded the limits, expected limits, and the challenges probabilistic seismic hazards model that assume regular recurrence. Now, again, talking about the engineering implications, super shear rupture underscores that long, straight crustal faults in South and Southeast Asia, including Indo-Burma, could sustain unexpectedly large, high-energy quakes. Hazard models for Northeast India must integrate the risks for this. Now, talking about the ground shaking and intensity of 2025 Myanmar earthquake, you can see a picture on the right. I just wanted to show what was the intensity of the shaking. So it was an extreme acceleration condition. At Nepido, as I've already mentioned also, the vertical acceleration reached up to 1.07 g, while Mandalay recorded about 0.62 g horizontal, and with the velocity being 161 centimeter per second. And these values indicate ground motions among the most extreme globally observed. So sadly for Myanmar, only certain cities had as the locations to measure this. So we have Nepido, we have Mandalay, and we don't have the data of the exact epicenter of the earthquake, Sakai, because they lacked some seismic record stations. And when we are talking about intensity, we are definitely talking about the population exposure. So you can see that over 70% of the population of Myanmar was affected by this, which experienced MMI 7 or higher. That means 70% of Myanmar experienced higher shaking, intense shaking. Of these, 5.8 million were experiencing violent, and 3.6 million were experiencing severe shaking. So this is as per the Merkia's range. Now, transnational effects. This is very important in our case. So shaking extended more than 1,000 kilometers from Imphal of India to Bangkok. So I'm just showing you the extent of the shaking. So it extended from 500 kilometer north to 1,000 kilometer of southeast. So it affected Imphal of India at moderate level, and also it at Bangkok high-rise buildings swayed for more than 2 minutes. So regional effects emphasize far-field hazard risks. So again, talking about the engineering lessons, remote but long shaking poses risks for tall buildings on soft soils, such as those in Brahmaputra Valley especially, and other Northeast Indian cities, design must consider long period ground motions. Now, talking about the impacts of 2025 Myanmar earthquake. So urban destruction, many areas of Mandalay and Sakai region were flattened. Critical infrastructures collapsed. I will show the pictures in the later slides. A key bridge in Irrawaddy River fell, gas lines ruptured, triggered widespread fires, multiple hospitals and pagodas were destroyed, and human toll at least 5,300 deaths and 12,000 injured in Myanmar. And this data is like updating with every time. So talking about the cultural heritage damages, over 8,300 monasteries and pagodas collapsed. Religious structure failed during the service, causing mass casualties. I wanted to bring this point because during earthquake or during kind of disaster situation, many people are tend to use religious structures for the immediate safety. But in Myanmar, it was observed that due to collapse of religious structure also, many casualties occurred. And economical losses, obviously, it caused 11 billion US dollars and making it the costliest disaster in Myanmar's history. Now showing you some photos of some damages. So you can see that the impacts on heritage and landmarks before and after. So I just wanted to bring you what are the impacts what are the impacts and intensity of the shaking and intensity of the Myanmar earthquake. So you can see before and after. These are some religious sites, and this is the on the right side you can see that this is the bridge I was talking about, the Irrawaddy River. It is one of the lifelines of Myanmar, and it was damaged during the earthquake. And obviously, residential and critical facilities were also damaged. You can see soft story. You can see a lot of damages. We will talk about the damages on upcoming slides. So we were able to assess more than 3,000 infrastructures, and also we got some data from other researcher friends. So what we were able to analyze is mostly the damages were small cracks on infill walls, and after that the large chunk of damage was moderate cracks on the infill walls, and beam and column joint shear failures were observed, and soft story effects and foundation failure were the least among the damage. So we saw these four types of, especially these four types of damages in the buildings. This is the data about the residential infrastructures, not about the religious. So you can see on the right side the beam column joint, the column is severely damaged. So now talking about the response versus design spectrum, MNBC, which is the design code of Myanmar. So I want to emphasize on this. This is the data from the Naypyidaw station, so which recorded the vertical of 1.07 G and horizontal speed in north-south direction to be 0.63 G and east-west to be 0.57 G. So you in the graph on my left you can see that three graphs. So these three are respectively being east-west direction, north-south direction, and a vertical direction. Up UD means up and down direction. So you can see. Okay, so on this response, this graph you will see five graphs in this. So these are the three: east, west, north, south, and up and down, and DBE and MCE. So these are the design spectrums of Myanmar. So what we observed is, for a shorter period, the vertical acceleration, the vertical shaking was more than the design. So because of this, small structures were damaged heavily. So you can see that in short time period, the green line is exceeding like 1.07 G. So it's exceeding the design spectrum. So because of this, shear failures of column, joint failures was observed, and short period shaking is damaging for low rise. So buildings, and in some areas of Sakhai, the whole community was flattened because of this. This was the main reason for that. So showing you how far, up to what distance this earthquake has hit. So you can see before and after. This is the Irrawaddy River bridge, which I saw earlier. So it was like 17 kilometers away from the epicenter. So this is a pagoda, which was again say around 17.5 kilometer away from the epicenter. This is again a historical structure which was like 19 kilometers, demolished completely. So when we are talking about damages, we are obviously, the big chunk of damage was in the residential building. So in residential building, we saw that soft story structure damage was a lot. So you can see on the right side how the ground floor is completely damaged, disappeared, of course. So this is the short video of Sakhai city, the city where the epicenter of this earthquake was. You can see almost all the infrastructures were damaged. This was, and you can see that the infrastructures are not that tall. It is like 3-4 story maximum. So you will see, because of that high vertical displacement, high vertical acceleration, the structures are completely damaged. So you can see the soft story, and you can see the infill walls being damaged. So this is on the right side, you can see the fire following the earthquake, because gas pipe a fault, the rupture passed through a gas pipe and the gas pipe busted, causing fire, because of which a lot of damage occurred in Sakai. And now, talking about the extent of damage, like damage in Nepido, which is like 240 kilometers away from the epicenter. You can see the damage. This is main hospital of Nepido, and this was designed to be very nice. The factor of safety was like more than 2.5, and you can see the damage, the extent of damage in this, and it is 240 kilometers away from the epicenter. This is another super center in Nepido. So you can see the damage. All infill of the columns are little bit intact, but all infill walls have collapsed. And this is in San state, which is 190 kilometers away from the epicenter. So I'm trying to show you the radius. Like I'll show you different structures. So it will be like 100, 200, 300 kilometers radius from the epicenter, which is Sakai region. So this is 190 kilometers away. This is Lake Inle, which is another like 200, more than 200 kilometers on the other side. Now, these was the damage in Myanmar. Now talking about the regional impacts. So regional impacts, it was not limited to Myanmar. So this earthquake was one of its kind because it caused damage very far away from it. So you can see that in Thailand, Bangkok, seismic wave traveled up to 1,000 kilometers to Bangkok, where skyscrapers swayed for minutes, and a 33-story under construction building collapsed, killing 92 workers. This highlighted how distance quakes can devastate poorly designed structures. The damage in Thailand was because of the soft soil basin which Bangkok possesses. Why I wanted to bring this here is because what we have seen in the literatures and from the past study is Brahmaputra also had similar basin. So if some earthquake occurs in Sakai in upcoming days, then this phenomenon can be seen. I will not say will be seen, but can be seen in those regions also. So again, in Vietnam also, widespread cracking and evacuation happened. In Ho Chi Minh City, we saw over 400 apartments develop severe cracks and required evacuations. While structural failure were limited, widespread disruption occurred, including one death from shock. And in China border, damages in Yunnan. Yunnan province shares border with Myanmar. So many homes were damaged in Yunnan province, bordering Myanmar. Ground cracks and minor damages extended even to distant western provinces. So this earthquake was one of its kind because of the long rupture, more than 500 kilometer, and long period of shaking. It has caused damage in very far away from the epicenter as well. So Myanmar's seismic vulnerability was exposed. You can see a community which was totally disrupted. This is the photo which was sent to us by one of the person living in this community. So why this happened? Why this happened? What are our initial observations? So Myanmar possesses weak construction practices. Talking about construction practices, despite the existence of Myanmar Building Code 2012 and updated in 2016, enforcement was inconsistent and many structures were built informally and with non-engineered masonry, poor materials, and little oversight. So these buildings collapsed in large numbers during the quake. And collapse of critical infrastructures. So basically, in any case, we want the critical infrastructures to sustain minor damage only, because those are very important during the disaster situation. But in Myanmar, it was seen that the key infrastructures, including hospitals, bridges, schools, failed catastrophically, demonstrating systematic fragility and no proper preparedness. Another big problem for Myanmar was the people of Myanmar were not prepared. Hundreds of people were affected and panic situation was created, which showed no proper preparedness and awareness about seismic activity and damages. It caused health and social vulnerability. Let me bring you to one incident. Like last year in 2024, there was an earthquake in Japan, Noto Peninsula earthquake. It was also more than 6, and it was also one of its kind, a severe earthquake. But the casualties were less than 10. But in Myanmar, the casualties, officially it is more than 5,000. Unofficially, we don't know, might be more. So why? Because the people of Japan were prepared. They have good early warning system. They have good awareness about seismic activities, awareness about infrastructures, but what we see is this was lacking in Myanmar. Also, as we have some experience about Nepal earthquake, that was seen in Nepal earthquake also. So now bringing you to the context of Northeast India tectonic and seismic context. So why I am trying to relate this to Northeast Indian context? Because Northeast India lies in seismic zone 5. So seismic zone 5, all Northeast Indian states, including Arunachal Pradesh, Assam, Manipur, Meghalaya, Mizoram, Nagaland, Tripura, and Sikkim, fall under zone 5, the highest hazard zone under the Indian Seismic Code, IS 1893. This is because of the tectonic slide which I showed you earlier. It also lies very close to the subduction zone between Indian and Eurasian plates, and also the two subplates. And plate tectonic setting, the region is bound by eastern Himalayas in Indian and Eurasian collision, which I just informed you. The Indo-Burma ranges, subduction and strike slip, and directly connected to the Sakai fault in Myanmar. The triple junction makes it one of the most seismically active regions on Earth. So now connecting it to Sakai fault, the Sakai fault that ruptured in 2025 lies adjacent to Manipur and Nagaland, meaning its seismic activity directly influences Northeast India. So strong shaking in Imphal during the Myanmar quake confirms this cross-border hazard. So if you all remember the previous initial slides, you can see that the Northeast India is like one of the coinciding zone for all the active tectonic plates on that region. So this is a cutout I took from Times of India of 6th January 2016, which says that disaster is in waiting. So 59% of Indian land mass prone to quakes, and you can see that the Northeast Indian states are in the very high risk zone, which is zone 5. So some parts of Bihar and Uttarakhand are also there, but Northeast India, all parts are there. So because this lies in the highest earthquake risk zone in whole India. Now, historical seismicity of Northeast India, talking about the historical seismicity of Northeast India. So this picture on my right, on my left, you can see these are the all past earthquakes in and around Northeast India. So this I took from a paper from Mr. Bora and Kumar published in 2022. So you can see a lot of seismic activities. Very few of them being more than 8, but you will see from 4 to 7 there are a lot of seismic activities each year. So one biggest recorded seismic activity for Northeast India was Great Assam earthquake. So Northeast India has experienced 2 of the world's largest earthquake. So in 1897 Shillong Plateau earthquake, which was recorded to be 8.3, and 1950 Assam Tibet quake, which was recorded to be 8.6. So these remain the most powerful in Indian history. So we don't have the record of damage at that time, and also the population density and urbanization was not that much. So maybe the damages were not that evident. And recurring large event since 1897, more than 20 earthquake of magnitude 7 to 8 range have struck the region, including 1946 Shillong quake and 1988 Sikkim quake and 2016 Manipur earthquake. So you can see in last 200 years, you have already experienced more than 20 earthquakes, big earthquakes, not the small ones. So ongoing hazard, I have been telling again and again, the Indo-Burma arc and the Eastern Himalayas continue to accumulate stress. Several segments have not ruptured in centuries, so suggesting high potential for future large events. So this is again probability. But it's highly probable. So now let me bring you to a case study of 2016 Manipur Imphal earthquake. So you can see this is the data recorded by USGS. A moderate earthquake with serious consequences. So it was a moderate earthquake. So this happened on 4th January 2016, and the magnitude was 6.7, and it was struck near Imphal at the depth of 55 km. So the moderate in size, it was widely felt across Northeast India and Bangladesh. Now, casualty and damage, the quake killed around 13 people, 8 from India and 5 from Bangladesh, injured around 200, and caused losses of around 41 million US dollars. So you can see a small 6.7 earthquake is causing damage of 41 million US dollars. Several buildings, including market structures, collapsed. So construction failures. So this is again summarized from the studies done after the earthquake by governmental agencies and some NGOs. So post-event analysis confirmed that poor construction quality was main cause of severe damages. Masonry walls lacked reinforcement, RC frames had weak columns, and new buildings failed as readily as old ones. So it is not that only old buildings failed, even the new buildings were also seen to be damaged. Again, talking about the engineering lesson which we got from 2016 Manipur earthquake. So even moderate earthquake can be devastating when buildings are not designed to zone 5 standards. So the Imphal disaster underscore urgent need for enforcement of seismic codes and retrofitting in Northeast India along with SHM for old structure. What is SHM? SHM is a technique which is being used these days. It is called structural health monitoring. So for important critical infrastructures, with the help of sensors, with the help of different techniques, so what we do is we keep on monitoring the health of the structure. So simply, in very simple terms, we measure the natural frequency in real time. So we can tell whether the structure is damaged or not. So now talking about the building vulnerabilities in Northeast India. So structural weakness under seismic load. So Northeast India, as per my research and as per the findings what I got, many rural and urban houses are on reinforced masonry or soft story apartments, highly vulnerable to collapse. And weak reinforced concrete frames. So RC buildings often lack ductility, proper detailing and shear walls, making them unsafe in strong shaking. Geological hazards, of course, Brahmaputra floodplain risks liquefaction, while hilly terrains like Shillong Plateau face landslide during earthquake. Now, Northeast India comes with another risk of multi-hazards. So if a seismic event occurs, it might trigger flood, it might trigger landslide. So code compliances, again, IS 1893 classifies Northeast India as Zone 5, which is 0.36 G design factor, but enforcement is uneven, leaving critical infrastructures at risk. So you can see this. This I got from a friend who sent me this, and this is just like 11 days ago. I think you guys experienced a earthquake, because of which this is in the some market of Guwahati. Sorry, I forgot the name. Some market of Guwahati. You can see this building being tilted. So on the so this building is completely tilted. So you can go through the YouTube channel and see this building. So this was because of earthquake. Sorry, I forgot the name. Phatasil market or something in Guwahati. So I just wanted to. So there are lot of these kind of structures I have also seen in Guwahati. Now, implications and preparedness for Northeast India, especially. So learnings, what are the learnings we got from 2025? Sorry, yeah. So anyone has some questions or something to say? Okay, we can continue. So implications and preparedness for Northeast India. Again, what are the learnings from 2025 earthquake, especially for Northeast India? So shared hazards. So 2025 Myanmar earthquake demonstrated that a major rupture on the Sakai fault can transmit shaking into Northeast India as well. Engineer must account for both local and remote fault sources when modeling seismic risks. So only local will, because this earthquake has exposed the possibility of long like far field seismic hazards. Like the Sakai fault was more than 1000 kilometers away from Bangkok. It was more than 500 kilometers away from Imphal, but strong shaking was felt in both regions. So what I want to bring in is we have to address the remote fault sources also when we are modeling the seismic risk. Again, cross-border coordination is very important. Collaboration with Myanmar on seismic data sharing, fault mapping, and historical earthquake studies can strengthen hazard assessments. And regional cooperation is essential for anticipating trans-boundary seismic risk. So it's very important to what we feel is the IS 1893, which says the design factor to be 0.36 G need to be revisited. It might need an update, because we have already seen in Myanmar earthquake that the vertical shaking was more than the design, more than the dB and MC. So this 0.36 G might need a revisit. So we need to use the data from Myanmar and from other regions to revisit those things. And infrastructure resilience, all new construction must strictly adhere to IS Zone 5 standards, while critical facilities like hospitals, schools, and bridges need urgent retrofitting. Techniques such as dampers and shear wall integration can mitigate collapse risk. And community preparedness is also another very important part for any disaster situation. So public awareness campaigns, school drills, and early warning systems are critical. Plans should integrate secondary hazards like landslide and flood triggered by earthquakes. Again, it's a very tricky situation for Northeast India, as I have been telling again and again. There is a multi-hazard situation, because Brahmaputra basin and the high hills of Arunachal Pradesh, or let's say this Manipur. So when an earthquake happens, or seismic activity occurs, there is a very high risk of flood, very high risk of land subsidence, very high risk of landslide. So we need to address the multi-hazard situation as well. And engineering leadership is needed. The practical engineers must advocate for enforcement of seismic codes and risk-based planning. Microzonation of vulnerable cities like Guwahati, Imphal, Aizawl is a priority for guiding urban safety. Microzonation, again, like for Bangkok, Thailand has already divided Bangkok into small microzones. So we are able to study the basin, soil basin. So it's very important for big cities and also the dense urban cities to do a microzonation and study. So this has brought me to the concluding part of my presentation. So talking about the lessons from 2025 Myanmar earthquake for Northeast India especially. So seismic threat is large and real. So Northeast India share the same colliding plate environment as central Myanmar, historical precedent. So this is 1987, I guess. And 1950-2016 Manipur earthquake confirms that large magnitude 7+ earthquakes are possible and it's inevitable. And shake, reach and amplification. Distant earthquake can produce long period shaking felt across region. Soft soil basins like Brahmaputra can amplify motion and threatening to tall and critical structures. So I'm telling this again and again because I believe that many tall structures which are being constructed in Guwahati might feel this threatening situation, because Brahmaputra basin, we feel that the Brahmaputra basin may amplify any signal it receives. So the tall buildings built in Guwahati, we need to be very careful about that. Again, vulnerable structures. Much of Northeast India's buildings are not earthquake resistant. This is again based on my own travel and my own observation in Northeast Indian states. So without immediate retrofitting and strict adherence to IS 1893 Zone 5 standards, catastrophic collapses are likely. And integrated risk management is necessary. So preparedness must extend beyond engineering. For example, land use planning, public awareness, and emergency situations are vital to reduce casualties and economic losses. So these are the lessons we got from Myanmar earthquake, and of course, based on this, we need to call for action. So the Myanmar earthquake is a wake-up call. Engineering planners and policymakers in Northeast India must act decisively to build resilience before the great earthquake may strike. I'll not say can strike, but may strike, because all the seismic studies says that it's in a high risk zone. So we need to take care. We need to understand, and we need to take the learnings from previous earthquakes, the Myanmar earthquake, the Turkey earthquake, the Gorkha earthquake, and Manipur earthquake. So we need to act as soon as possible. So this brings me to the end of my slide. So with acknowledgement, with gratitude to Professor Dr. Swetambara Burma, HOD ma'am of Royal Global University, Mr. Rishikesh Dura and Ms. Raisa Tamsin, the assistant professors of the the Assam Royal Global University, and big thanks to Atal FDP program for giving me this opportunity. So what I want to end it with is a wake-up call to rethink our earthquake readiness, because I keep on telling this in whichever platform I get chance to speak, that earthquake doesn't kill. Our preparedness, our ignorance, and our non-coherence to the codes kills people. So please take it as a wake-up call. You can see this pagoda being dismantled. So please adhere to the codes. We need to act, and we need to act very soon. Thank you, everyone.
Thank you, sir. With this, I would like to open the floor for questions, and
Yes.
if you would allow us, yeah.
Yeah,
So
yeah,
I would request the participants to unmute themselves and ask the questions if they have any.
So if they have something, they can write on the chat box also.
Yeah, they can write in the chat box too. Participants, if you have any questions, you can ask.
I have already shared the slides with Ms. Raisa for the participants. So this is the tectonic map which I was talking about. So you can see, yeah, this is the red one. Red one is the subduction zone between Eurasian plate and Indian plate. So you can see Mandalay being here, and a big part passes through Northeast India. So you will see a lot of seismic activity here, and the slip rate is also more than 18 mm per year. Okay. So we got a question from Rishikesh sir. What are some of the ways to mitigate the soft story effects of structures on structures during earthquake? What retrofitting method suits best for Northeast India? Okay, so if we are talking about soft story effects on structures, so soft story is kind of inevitable for us, because in our culture what we do is we build 3 story houses, 4 story houses, and we put a kind of a opening on the base, ground floor, because of which we have observed that a lot of soft story occurs. So there are different techniques to retrofit these structures. So the most relevant and easy techniques might be column jacketing, or maybe strengthening the base column. And we are doing a lot of research here at AIT on this soft story, how to do the retrofitting of soft story structures. So what we are doing right now is, so if you can see my screen, so this is a typical structure of houses in our places. I'm talking about our means, like in Nepal, you'll see in India, in Pakistan, many places. So this will be occupied. This will be occupied for living. And you will see this is used as a shop, or as a parking, or anywhere. So this will cause soft story, because this will experience the most higher stress. So what can be the best way is we design it properly, and this and another big mistake, I will say, what we do is the columns are uniform. The columns are uniform in our case. So we need to make this column more stiff. We need to make these columns more stiff. So we need to make these column more stiff. If for a already built structures, column jacketing or what maybe reconstruction of this column can be a effective method. And what we are doing at AIT is we are optimizing the structure. So what the group is doing is first they will first they will model first they will model the structure with whole walls. Then they will open a certain part. Sorry for my drawing. So what we will do is we will open the part. We will create another model with certain opening. Then we will create another model with certain opening. So we keep on optimizing. So at last we will find the best optimum solution. So right now what we have found is right now what we have found. So right now what we have found is a structure like this can be the best solution for this. Arch, arch, arch can be the best solution for this to counter the soft story effect. So we develop a arch action. Okay, no worries. So we develop a arch action. Similar on the both sides. We develop what we do is we drill the column. And we embed rods, and we create a mesh, and we pour concrete. So this can be a method where we can use the opening for your purpose as well, and then we can also counter the soft story. So what software can be used for modeling? So right now we are using ELS. It's called extreme loading of structures. It works on AEM principle, and you can also use some FEM softwares like SAP and the ETAPS and Perform 3D. Perform 3D especially is able to do this. So ETAPS, the new version after 2022, is able to do this. You can use this. Were there any notable examples for building or infrastructure that performed well during Myanmar earthquake? That's a very good question, Dr. Snail, but we didn't get good examples, because for Myanmar one issue was we are not able to get enough data, and on ground visual assessment was also very critical due to the political situations. But we believe that there are some infrastructures which have performed very well. One of my friend was telling me that there are some structures in Nepido which we have not able to get the data right now, but definitely if we get, we'll be sharing with you. So any more questions? Is there any specific code in Myanmar? Yeah, I have already mentioned. It's called MNDC. it was formulated in 2012 and it was updated in 2016. It was updated in 2016. So the DBE and MCE I showed you was for the code. Let me go to that slide. Click करो. I know. Mouse ले click करो. Voilà. छुट्टी तो होता. So if you are talking about code, let me go to that slide. Oh, okay, this one. So this is the code MNBC 2020. So they are using this design code for earthquake resistant design, but after this earthquake, it was seen that the vertical acceleration exceeded the DBE and MC for the very short period. That's why we see that the low-rise building up to 4 story were damaged a lot in Myanmar. Any more questions?
So no more questions, I think, in the chat box.
So I have also mentioned my email and LinkedIn in my slides on the last slide. So if you have any questions, any suggestions, and anything to share also, we are always ready to collaborate. We are always ready to share the platform. Please feel free to connect anytime you like. Thank you.
Thank you so much, sir, for your insightful session. And definitely we all had a great time. And with this, thank you so much. And we would conclude this session.
I
Thank
just
you.
want to thank our resource person. So since he joined from abroad, and indeed it was a wonderful and insightful session, sir. We sincerely thank you for gracing us and accepting our invitation to join from your busy schedule, you have taken time. So thank you. Thanks a lot.
Thank you so much. Thank you, ma'am, for your opportunity. Yeah. See you. Thank you so much. See you all.
Dear participants, do not disconnect yourself. We will start with our next session in some time. So probably we can take 5 minutes break in between before we start our next session.
The next speaker will join at 7:15. So I think everyone can take a break for 5-10 minutes.
So maybe by 7:10, we can all come back and then wait for the speaker to join.
We can, something about the speaker, we can announce, like the speaker is joining from
Yeah,
US.
the speaker
Because
is
of the time constraint, basically.
yeah. The
The
speaker has joined from the abroad, as in he is based in US, and that is exactly the problem. And so we're not being able to tell him that the speaker has finished. So can you join our session right away? So that is the communication issue here. So I hope the participants understand. We'll start in another 10 minutes. We'll come back. Thank you. I request the participants to, or maybe um, we can ask the participants to join back.
Okay, Ketan.
Hey, good evening there. Can you all hear me?
Yeah,
Yeah.
All
so
right,
we
great.
can begin the session.
We will begin the session in a while, sir. Just taking a moment here as we took a break of 10 minutes. We are waiting just for another 2 minutes for our participants to join back. Well, can you just put this message in WhatsApp?
Yeah, I'm doing that.
In the meanwhile, is it okay if I try and share my screen so that
Yeah.
we can check the modalities if they're working or not?
Sure.
Let me know if you can see the screen right now.
Yes. We
All
can
right,
see the
perfect.
screen. Yeah, Dr. Ketan. We're starting in a minute.
Sure.
Yeah, I think we can start. So, let me just begin with a note here. So this technical session here is to be delivered by Dr. Ketan Ragalwar. Dear participants, and Dr. Ketan, please give me a minute to introduce you to our participants. Dr. Ketan Ragalwar is a licensed professional engineer, structural, with over 16 years of combined professional and research experience in the analysis and design of critical infrastructure, including dams, bridges, marine structures, and power plants. He earned his PhD in structural engineering from the State University of New York at Buffalo, where his dissertation focused on the development of advanced cementitious materials such as ultra high performance concrete UHPC for impact and blast resistant structures. Dr. Ragalwar's expertise spans experimental evaluation of UHPC, full-scale structural testing, and risk assessment of high-hazard structures. His unique background, bridging advanced research and applied engineering, makes him well suited to speak on the latest guidelines for structural design with UHPC, particularly with respect to flexural and shear behavior. We are truly honored to have you with us, and I, on behalf of the team, warmly welcome you and hand over the session to you.
All right. Thank you, everyone. Thank you for the introduction. And good evening and namaskar. As Christy introduced me, my name is Ketan. So today's agenda is basically focused on the flexural and structural guidelines for UHPC based on the FHWA guidelines report, and then which was also formalized by ASHTO. However, I'll give an overview of ultra high performance concrete and its properties. We'll talk about some mixed design methodologies, as it is critical to understand what are the ingredients, what makes UHPC different from conventional concrete. So we'll talk about briefly about some mixed design insights. We'll then focus on mechanical properties of the UHPC, especially which are commercial products such as ductile by Lafarge and other products which are more or less very standardized and used in the United States. We'll then focus on how these mechanical properties are taken into consideration for flexural design. Um, Talk about some implications on shear design. We'll talk about an example for flexural design based on the FHWA guidelines. And we'll then spend some time looking at what seismic design considerations we'll have. And then I'll open it for questions and answers. So, thank you for the introduction again, but I'll give you a brief introduction for myself as well. I completed my Bachelor of Engineering from Nagpur University in 2005, after which I pursued a Master of Technology in Structural Engineering from NIT Nagpur. Later on, as Christy mentioned, I worked in nuclear power plants, thermal power plants, structural engineering, especially focusing on concrete structures, and that kind of led to interest in research in concrete structures and concrete material, after which I embarked upon a journey to complete my PhD from State University of New York at Buffalo. My dissertation focused on systematic development of advanced cementitious material, which was more focused on developing mixed design methodologies for the structural performance. So, for example, we were tied with very few mixed designs, such as I mentioned on Lafarge and other commercial products. However, those came with very fixed concrete strength and very fixed tensile properties. But as you know, based on our structural performance, structural analysis, we are driven by what grade of concrete we want to use, what compressive strength we want, what kind of sizes we want, and then that analysis determines the concrete properties we want to have. However, we are limited with the concrete properties here. And even more than that, the concrete properties are governed by very specific ingredients. So that led to uh, very high values of cost. So we wanted to develop a methodology where you can use local ingredients and still achieve high properties. And the later half of my PhD concentrated on structural evaluations of the materials that I developed from the mixed design. So after my PhD, I have been employed here in as a licensed professional engineer in the state of New York. I was also employed with FHWA at their Turner Fairbank Highway Research Facility, working on ultra high performance concrete, specifically looking at some post-peak behavior of pre-stressed girders. So that was the introduction for myself. So we'll talk about ultra high performance concrete now. So before that, what we'll look at the baseline. As baseline, we know normal weight concrete comprises of cement, large aggregates, fine aggregates, and water typically. Sometimes based on requirements, we also add different admixtures, such as for increasing viscosity or increasing workability, increasing or delaying the setting time. So these are different admixtures that we use. In 1970s, there was development of high strength concrete and also self-consolidating concrete, which further led to the understanding that large aggregate, when basically concrete gains its strength from the aggregates which are binded together by the cement paste. So the concrete strength is usually as good as the strength of the cement paste and the inherent flaw. So what do I mean by inherent flaw? So if we look at the fracture-based model for concrete, um, we observe that basically concrete paste binds the aggregate together. But the larger the aggregate, larger is the flaw size. So that flaw size determines at what stress do we see the initiation of failure in concrete. Okay. So if we keep on reducing the flaw size, then we see higher strengths. And that's how they determined, or they came across, that eradicating large aggregates and focusing on smaller aggregates will lead to higher strength. With that also came advent of using supplementary cementitious materials such as silica fume. So supplementary cementitious materials such as silica fume basically worked on the hydration products. So the byproducts of hydration further react with silica fume and form supplementary hydration products which give higher strength, which is known as CSH, which we'll see in the next slide. So that CSH, along with the lower aggregates, does two purposes. It increases the strength of the paste, and it also reduces the flaw, which basically reduction in flaw means higher stress is required to initiate a crack or failure in the concrete. So that led to advent of achieving very high strength up to 30 ksi or 21 ksi. 21 ksi means 150 MPa. So when the concrete paste started, or newer concrete materials which were known as ultra high strength concrete started reaching these high strength, they also realized that towards failure, the failure is very sudden and catastrophic. So basically at higher strength, there is no post-peak behavior in ultra high strength concrete. As soon as the concrete breaks, it just disintegrates uh, into fragments. So they started adding fibers into that to have some kind of post-peak slope to it. And later on, they realized that with experiments that these fibers not only contribute to a post-peak compressive behavior, but also help in some kind of tensile strength. So today's ultra-high performance concrete, which is basically cement, silica fume, fine aggregate, water, admixtures, and fibers, uh, have no large aggregates. They include short discontinuous fibers. They include higher end water reducing admixtures because the water to cement ratio is very low. Again, water also is an inherent flaw. So when water is added in abundant quantity, it gets stored as a gel in concrete, and upon drying, it also creates voids, and those voids are also flaws. So another way of increasing strength is also lowering the water content. So with very low water content, it's difficult to mix and have workable concrete. So that's where admixtures come into picture. So UHPC class materials are cementitious based composite materials with discontinuous fiber reinforcement. Compressive strengths of above 21.7 ksi, which is equivalent to 150 MPa, and they have a pre and post cracking tensile strengths of above 5 MPa and enhanced durability via their continuous pore structure. So you can see in this picture that how conventional concrete looks against a UHPC class material. So UHPC class material has very low pore structure and very discontinuous pore structure, whereas and it also has no larger aggregates which can be seen in the conventional concrete. But that's why we see this difference in conventional concrete and UHPC behavior. So the first plot is axial strain versus axial stress in compressive behavior, and the second plot is under tensile loading. So we can see there is significant tensile strength in UHPC, and it also has some post cracking behavior in tensile strength under tensile loads. What are the benefits? The benefits are that we can come up with much slender design. The dead weight of the structures is low. It can be used in coming up with unique structural solutions. So this is a precast UHPC beam and piers in a bridge that was built in Montpellier in France. Um, and also it comes very because of its uh, coherent and very dense structure, it is able to form very good bond with the reinforcement, and that's why this is a picture that shows conventional details of cast in situ joints with precast members. So you can see how dense is the requirement for concrete reinforcement in a conventional detail, but whereas UHPC details requires very less development length of the reinforcement, and therefore it saves on a lot of reinforcement. Not only that, with 21 or 150 megapascal strength of concrete at 28 days, it can achieve very high strength within 7 days. So this kind of detail is also used in accelerated bridge construction, where you bring in precast members and connect them on site, and within 7 days, the traffic can be opened rather than waiting for longer times. So with that, we'll briefly discuss about UHPC mixed design philosophy. So I talked about a homogeneous microstructure. So uh, uh, um, the strength in the concrete paste is provided by calcium silicate hydrate. And that's where, to maximize the proportion of calcium hydrate, silicate hydrate, we add supplementary cementitious materials such as microsilica or silica fume, which I talked about. There are other materials such as ground slag or fly ash, which also combine, but they have other other properties as well, which can be, detrimental or not as advantageous, I should say, as silica fume. Then the second point is minimization of number of slice and for number of and sizes of loss. So that comes by lowering the water to binder ratios and eliminating coarse aggregate. And then the third one is dense particle packing. So dense particle packing also leads to self-consolidating behavior, which requires lower water to cement ratio and also eliminates any kind of flaws. So as I mentioned, most of the UHPC matrix designs only incorporate one or two of these design principles explicitly and achieve their test through trial and error method. During my PhD, I came up with a model that incorporates the modified Andreessen-Anderson method. So this was previously developed um, to look into particle packing model. What it says is that that D is the aggregate size, and so maximum aggregate size and the minimum aggregate size in the ingredients uh, are used to determine a cumulative curve. So what these curves mean is that lower the distribution modulus will have higher paste content. And if we have the higher distribution modulus, what it does is that it increases the ratio of gravels to powder. So in general, you would see that the UHPC distribution modulus is in the range of 0.25. That means we have higher paste content. And that also comes into fact that paste content is defined by anything lower than 50 microns. So cement particles, silica fume, other things that contribute to paste content, and then the lower aggregate forms the gravel or powder ratio. So we take into account different particle size distributions such as sand, cement, slag, microsilica, and we set a target curve. So target curve is smooth curve, which is defined by this equation here. And what we try to do is that we form a cumulative, which is shown in this black curve. This black curve is the cumulative particle size distribution when you proportion sand, cement, slag in certain proportion. So if you have sand to cement ratio as sand to cement ratio as 1.5, slag to cement ratio as 0.6, or microsilica at 0.5. So you take these different proportions and draw cumulative curve. So that is known as the mix curve. And then this is the target curve, which is defined by the value of Q. So the idea is by proportioning or changing the proportions of these weight proportions of different ingredients, you can minimize this error EJ, and that brings you as closer to your target curve. So that process is fed into what is known as an experimental design. So here SCM is any kind of supplementary cementitious material such as silica fume or slag or fly ash. So rather than conducting, abundant number of tests, we came up with a philosophy where we can conduct 9 points. So these are 4 plus 4, 9 points on a plot, which is water to binder ratio and supplementary cementitious material to cement ratio. And then 4 additional experiments are conducted at the central point. So this is a philosophy that is commonly used in experimental design whenever our experiments are conducted with 2 factors. And then for each point, we do a mixed design, which I talked about in the previous slide. That gives us the mixed proportion. And then those mixed proportions, we conduct experiments, we measure compressive strength, workability, or any response. That response can be plotted on Y curve. And then the factors that we chose for the experiment can be plotted on X and Y curve. And then this is on the Z curve. So it gives you a quadratic equation that is relating both the parameters that you chose for experiment and gives you a relation between the response, which can be compressive strength or workability or any other parameter, with and its relation with the factors that we chose. So what it does is that I don't have to conduct an experiment or a point on all the different domains. I can use this curve now and say if I want to have, if my design warrants that I use more slag because I want to substitute higher cement and I want 120 strength, compressive strength, what would be the water to binder ratio that I want? So that gives you, a formulated values. So that is really, helpful or is supposed to be helpful in doing the mixed design. And then comes the final element, which is fibers. Commonly used fibers are steel fibers in USPC. They come in different aspect ratios and also morphology, such as hooked fibers or twisted fibers. Usually their length is between 12.5 to 225 mm and diameter is 0.2 mm. And then we can also use polymer fibers in UHPC, high density polymer fibers such as HDP fibers almost have as high tensile strength as steel fibers, but their diameter is almost an order of magnitude, 2 orders of magnitude smaller. So HDP fibers, for reference, is even thinner than our human hair. So what that does is, for the same fiber volume, the count of fibers is over 200 times of steel fibers, and that gives you more bridging between, excuse me, bridging between concrete when the concrete cracks. However, the downside is that these are difficult to mix, and you need specific viscosity. You need to control the viscosity of the paste so that these fibers are uniformly dispersed, or any polymer fibers are uniformly dispersed in the concrete, because as per definition, as you remember, the UHPC contains discontinuous fiber reinforcement, and it should be randomly dispersed. So now we look at the UHPC mechanical properties. So to begin with, this is how a typical conventional concrete would look like. So I wanted to, in the introduction, I wanted to mention that most of my plots here are in what we call empirical units. So these are in PSI and KSIs, which is kips per square inch or pound per square inch. Roughly 7 kips per square inch would give you 50 MPa, or 21 KSI would be equivalent to 150 MPa. So as we move forward, these would be the units that I would be referring, and excuse my, and excuse me for that. So That was the plot for conventional concrete. You would see that it has a more defined post-peak behavior up to certain strain limit, and 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 that's why in IS code we have a sort of rectangular parabolic stress strain curve for concrete. However, the UHPC has distinctly different behavior in compressive strength. It is almost linear until it reaches its peak, and then after the peak is arrived, it sees a sudden drop. So this is idealized curve, and that's why when I plotted it with Excel, it gives me a very smooth plot. But you would see that the fall after the peak is very sharp. So the compressive strength is very high in UHPC. We see a sharp drop in compressive strength after post peak. Um, Fiber bridging capacity arrest the sudden drop, and the stress kind of plateaus around 7 KSI. So you would see in this plot compared to conventional concrete 6 KSI plot that UHPC is almost linear, then it drops suddenly and kind of plateaus. Okay. Now we look at the unique feature of UHPC, which is its behavior under tensile loading. So this plot here is what is known as the response for uniaxial tensile test. So uh, on the y-axis we have tensile stresses in MPa and average tensile stress on x-axis. Uh, so the first phase, when we start loading it under the uniaxial tensile loading, is we see that there is a straight rise in the stress with increase in strain, and that is almost linear. So that is phase one is elastic behavior. And generally, the cracking strength, which is the first cracking strength here, where we see a sudden drop, is empirically thought to be equal to this value here. The phase two is where multiple tightly spaced cracks form in UHPC matrix. The cracks occur individually as the stress in the matrix exceed the matrix cracking strength. So once the matrix cracks, that is matrix meaning the concrete itself, it cracks, the discontinuous fiber starts bridging the crack, and if there is enough bridging capacity in the matrix or in the concrete, what it does is that it allows to concrete to crack at some other location. Okay, then again at that another crack location you would see fiber bridging, and again at that crack location, if we see that fiber bridging capacity is higher enough to initiate crack at a third location, and then we see multiple cracking until we reach phase 3, where you see that there are no additional cracking, but individual cracks starts widening. So there are no more cracking. So at this point, we have probably exhausted what is the fiber bridging capacity. And now we are seeing what is known as localization of crack. So phase 4 would be where one individual crack completely opens up, and then you would see that fibers are completely pulled out at crack, and basically just opens up, and then you would see that unable to bridge it, that localization keeps opening, the crack keeps opening, and the neutral axis kind of keeps going up, and basically we see almost sort of hinge formed, or not hinge in this case, but we see complete pull out of fiber. So this is uniaxial tensile. But this uniaxial tensile behavior also leads to varied flexural behavior, which we'll see in the next case, depending upon whether the behavior under uniaxial tensile test is strain hardening or strain softening. So in a strain hardening concrete or fiber reinforced concrete, basically the fiber bridging strength where localization occurs is greater than the cracking strength. So this localization maybe it occurs here because we don't see the concrete strength, tensile strength increasing again. So this, if it is higher than the first cracking strength, then you would see multiple cracking, and it is known as strain hardening. So this is how a typical behavior in or a response looks like with different parameters. What I'm going to play a video here, which shows uh, the response of. So I'll increase the speed. So this is a beam tested under 4-point loading. And as I said, the tensile response is governing the pure flexural behavior. And you would see in this video how multiple cracks are formed, how the fiber bridging is. So this is where the first crack appear. You would see cracks propagating up to what is probably neutral axis depth. And in this location, you would see that all these cracks are forming, but they are still being bridged by the fibers that are crossing. And that bridging capacity is sufficient enough for another crack to develop. And when you have really high bridging capacity, along with lower fracture toughness of the concrete, that keeps that helps concrete form multiple cracking. And because of this multiple cracking, uh, it shows what is known as pseudo strain hardening behavior. And therefore, we can see that pseudo strain hardening behavior translate into um, deflection hardening as well. So what is deflection hardening? It is after the first crack appears in deflection, you see that the beam is able to take higher loads. Okay. And this is where the localization has started occurring. So you would see that this crack particular has completely opened up. So we have talked enough about the tensile and compressive behavior. How to use them? There are structural design guides or design guidelines that are being developed in all over the world currently. So ACI has a committee 239 which is developing guidance. Switzerland, I think, already has a specification that defines material classification, design, and execution. So does has France. Japan was probably the first one to come up with recommendation and guidelines, especially for defining tensile behavior. In the US, FHWA came up with 2023 in 2023 with structural guidelines, and then those were submitted to AASHTO, and then AASHTO came up with their first edition of guide specifications for structural design with UHPC in last year. So today we are going to focus on those two. So I'm going to talk about how AASHTO and FHWA defines material parameters, because to use these guides, you need to have minimum specifications in the materials that can, define it as UHPC. So the minimum compressive strength of 17.5 KSI, a minimum effective cracking strength of 0.7 KSI, a minimum crack localization strength greater than or equal to effective cracking strength. So that is a requirement. So it cannot be a strain softening. That means a crack happens and then tensile strength continuously dips down. That is that kind of material we cannot use this guideline for. And then a minimum crack localization strain is also defined. So if we look at this video here that we talked about, this is localization where one cracks open up, and then the strain related to at that location is known as localization strain. So this is a standard setup for performing a uniaxial tensile test. Basically, it's conducted on on a prism which is 2 inch by 2 inch, and the length of the specimen is 17 inches. Those are gripped on either ends, and then you subject that to tensile stresses or tensile loading. So we can see that there are usually two types of curves that we can see. After the first crack, either it kind of maintains that stresses and then crack localization occurs. And we can see that stress at crack localization is almost equal to stress at cracking, whereas on the red curve, that another specimen curve that we have, we can see that crack localization is higher than the first cracking. So the compression design model, we know that in Indian codes, we have a kind of a parabolic model that we use. In the US, they used a rectangular concrete stress block to define concrete behavior. Here, because of the post-peak behavior of UHPC, the FHWA recommendation is to use a bilinear model. So the first part is a linear model with the strength increasing to factored compressive strength linearly, and then this strain limit is defined by the modulus of elasticity, and then basically we truncate the strength at that level and define it up to the limit of compressive strain. So if we look at this typical model, we first basically idealize the linear part of it. Then we determine what is the factored compressive strength, and then the strain related to that is the plastic limit. And then at the crushing strain equivalent to crushing strain of concrete, we basically draw a horizontal line and cap it at that location. Okay, in terms of tensile behavior, the effective tensile cracking strength is the onset of the formation of first crack. And then crack localization, which is another parameter that is used to define the tensile behavior, is basically the first tensile stress value at which tensile stress continuously decreases with increasing strain and permanently drops below the value of effective cracking. Okay, so again, as I mentioned, and basically the strain related to that is localization strain. So the first cracking or the cracking stress after which uh, the stress with increasing strain does not, rebound, it just keeps lowering. That the strain related to that stress is known as localization strain. So all these parameters which go into defining the tension block of the concrete are basically in another ASHTO guideline, which is T397. So this guideline basically defines how the experiment is to be performed, what are the strain rate and or loading rate of the specimen, how to document each behavior, how to calculate averages over number of specimens, and then basically how to define parameters that can feed into the structural design. So this is a 397 which was released in 2022. Okay, and this is the plot we had talked about, which I have shown you previously. Here are all the parameters. Basically, this is the elastic limit, after which we see that it becomes nonlinear. Then the first cracking happens. As we keep increasing the strain, we see it reaches a peak, which is the value. And then further, as we see, even after reaching peak, when it drops, it kind of gains. So that's why we did not define localization here, because as the crack kind of opens up, there was another crack form, and then it helped the stress to reach higher with increasing strength. But at this point, we can see there from this point onward, basically it never regains any strength or any stress level. It just continuously keeps dropping. So this is the point where we define localization. Okay, so so those are the parameters that we use to define the tension design model. So there are two tension design models here to account for strain hardening. So with UHPC materials where the localization stress is uh, lesser than 1.2 times the cracking stress, we use the bilinear model with kind of elastoplastic behavior. Okay, so we cap the stress limit at factored first cracking strength, and then that stress block is extended up to a factored value for localization strain. And then for another one where we see very strain hardening behavior, then if local stress at which localization occurs is higher than or equivalent to 1.2 times the first cracking strength, then this is the model we use. So we apply factors of safety to to cracking strength as well as localization stress, and then the strains are equivalent to the cracking strength, which is given by modulus of elasticity, and then we also have localization strain. So these are two different blocks. So this is unique as compared to conventional concrete, because in conventional concrete, we just above the neutral axis, we use the rectangular parabolic stress block or rectangular stress block. And below the neutral axis, we completely ignore the concrete and we just use stress in steel at their centroid of the steel placement. Okay. So there is nothing below the neutral axis. But here in UHPC, we have to account for the tensile stresses below the neutral axis in concrete as well. So we'll see that further. It is important to understand why this localization strain is important. So these are the three different tests carried out at what is the longitudinal reinforcement effect. So you see that that stress localizations happens in all the different beams, but that basically leads to very different behavior in their under flexure behavior based on the reinforcement. So the amount of reinforcement placed also dictates how the behavior changes and how localization is detected. But it is a varied behavior. It is very difficult to cap, and that's why the reason that I'm showing this slide is to show you that based on the reinforcement, based on the fiber distribution, because we can see that there are two different fiber distribution. The blue color is having 0 fibers, whereas the red color plot shows 2% fiber. So it shows that based on the fiber amount, based on the reinforcement amount, the behavior of the beam under flexure is very different. And to capture that uncertainty, they introduced this capping of behavior of tensile block at strain localization and applied a factor to it. So this is also a good plot which shows how the behavior is different in UHPC and high strength beam, reinforced high strength concrete beam. So here we see lesser number of beams and concrete crushing. Here we see that crack localization leads to fracture of reinforcement in the fiber. So the failure modes are very different based on presence of fiber. And that's why to answer that question, when and where does the crack localization occur under flexure loading, it's difficult to answer that question. And as a design guidelines, they try to cap it, but also take into account that we are considering the block under tension at least up to crack localization, because if we ignore that, then we are basically not utilizing the material to its fullest. So this is a typical plot for moment curvature. So moment curvature is used to also used to define uh, uh, the uh, uh, the performance of flexural elements, and we see that this moment curvature curve is defined by 4 points, which is... Yes, any question? I thought I heard someone. So this is the first point is defined by cracking. Second point is defined by a service level stress. Third point is yielding of reinforcement. And the fourth point is, I have written it here. So the fourth point is basically localization. So nominal cracking is the nominal moment and curvature at which, um, cracks initiate, and then nominal flexure moment where steel is at its steel service stress limit, that is defined as MSL, and then yielding and localization. And then once we have those values, we use the ductility in the member to define what is nominal flexural strength. So in the example, I'll talk about it. So now we have different UHPC compression model, UHPC tension model, and steel reinforcement model. These show, stress blocks and how we can use this. So now we know that uh, this bilinear model of compression and tension basically are used above and below the neutral axis. Okay, so the first plot here is the elastic stress distribution in compression block. So that means our strain in extreme compression fiber is lower than the plastic limit. Therefore, it stays linear. Okay, the stresses are linear. However, with this stress distribution, we see that below the neutral axis, there is a bilinear model. Okay, so in conventional concrete, this won't be present. You would just have this longer arrow which shows the reinforcement. Okay, as the as the curvature in the beam is increased due to the loading, we would see that the strains exceed the plastic limit in the extreme compression fiber, and that's where the bilinear model of compression will come into the picture. So basically, instead of this linear model, we would have a bilinear model like this, and then below the neutral axis, we already had a bilinear tensile model. However, you would see that that based on the strain distribution and on localization, this might change. Okay, so after this, the evaluation or calculation of the moment sustained by the beam is straightforward, as we do the summation of forces. We calculate the neutral axis so that the force in the above the neutral axis and below the neutral axis are same, and then we calculate the moment based on the forces below and above. Okay. So the structural design with UHPC for shear design is very straightforward, and I'm going to cover it in just one slide very briefly. So basically, what is different here? Now, if we go back to our first slide, we saw that we had no large aggregates, and the concrete shear strength comes from the interlocking of the aggregates. So there are no large aggregates. That means there is no interlocking presence here. But instead of that, we have discontinuous fiber, which gives strength carrying capacity under tension to UHPC. So that they have modified the basically come up with modified compression field theory, and used it to calculate the requirement of transverse reinforcement. So the contribution from UHPC here is basically coming from the tensile strength given by the fibers, and it's the procedure basically evolved around calculating theta, which uses a bunch of equations here, but there is a straightforward way or simplified approach where for members with module of elasticity greater than 6,500, and then if you have a localization strength or stress lower than 1.8 KSI, then a table from 1.2 appendix 2.2 can be evaluated to determine this theta, which is the angle at which the shear failure would occur, and basically forces are resolved, and that would give you that takes into account the discrete reinforcement strength provided as shear reinforcement and gives you a total a factored shear capacity. So there are two processes. For complex beams or slabs, you can use generalized approach where you want to calculate parameters theta based on modified compression field theory. But for simple, straightforward rectangular sections, you can use simplified approach. Now we'll look at section analysis. So I have taken typical parameters here, which are shown. So basically a compressive strength of 22 KSI, and typical steel reinforcement properties. Important to note here is that first cracking strength of 1 KSI, similarly localization stress of 1 KSI, and strain of 0.03. So these are the models. You would see the compressive strain limit is at crushing is 0.0035, and then it is capped at 18.7, which is the factor of safety. And similarly, strain model for tension. So this is the first point in our plot. If you remember moment versus curvature. So what we define in the first plot is that we put the strain at the extreme bottommost fiber equivalent to cracking stress. So that would give us a strain distribution. Based on that strain distribution, we calculate stresses, and that will will evaluate moment based on that. The second point, the second location is where we arrive at what are or evaluation point is where we basically equate the stress in steel reinforcement equal to service limit. Now, service limit in ACI or ASTO is defined as 0.8 times the yield value. So yield strength of this reinforcement is 60 KSI, so that would give us 48 KSI. So 48 KSI would give us some strain value in the steel, and that strain value in the steel is considered at this location, and a strain profile is built. Once we know the strain profile, we can calculate the stresses and again calculate what is the resulting moment. So the third point here would be yielding of reinforcement, and that's why we see from 48 KSI, we have increased the value in steel stress as 60 KSI, calculate equivalent strain here, determine the strain in extreme fiber on compression and tension side, use our model. And then you can see in all these models, we have up to this point, we have linear stress block in compression owing to very high strength of concrete, but in the tension we have bilinear model. And then at the last point we have extreme fiber as stress localization. This is where beyond which this cannot the stress block cannot proceed. Even then we have stress as linear in compression block. However, the value has increased from somewhere close to 9.01 to 9.98. And the last value we will calculate to build our moment curvature plot is equating extreme compression fiber strain equal to crushing strain. So at this point, we will see finally we can have the bilinear model in compression. However, the stress localization occurs much above the extreme or the bottommost fiber. So therefore, we have stress block extending under tension up to only a partial point. And then, of course, we have the contribution from steel. So this is how we would find out the location of neutral axis, equate the forces, calculate the moment, and then basically plot it. So this is how usually a plot would look like. This is the first cracking moment, then the service. Then we would have the service moment. Then we'll have what is known as the crack localization, and then this is the compression crushing. Okay. So what is the factored resistance? Now, factored resistance is basically calculated based on curvature ductility. So whatever is the nominal capacity, we divide it basically using the curvature at service limit. And then we use ductility ratio, and that ductility ratio is used to calculate a resistance factor using this formula. And based on this resistance factor, we multiply the localization moment with that resistance factor, and that will give you a factored resistance. So I explained the whole building of moment curvature because that is how it is used to calculate what is the factored resistance, what is the resistance that we should be utilizing to design our beams. So moving on to our last part, we'll talk about seismic considerations. So as we have seen till now, unlike the conventional reinforced concrete, which typically fails through cracking, reinforcement yielding, and then crushing or fracture, reinforced HPFRCC exhibits two distinct failure paths identified by research done by Shaw and Billington. The first path is basically failure after crack localization. In this case, the crack initially forms through multiple fine cracks due to pseudo strain hardening behavior. When the fiber bridging weakens at the most critical crack, localization occur, which we have talked about. Okay, if reinforcement hardening cannot fully offset this loss, beam's capacity also drops after localization, ultimately leading to reinforcement fracture, which is happening here. Okay, at this X. The second path is the path which is on after failure after gradual strain hardening. In this, reinforcement continues to gain strength even after crack localization. As a result, the beam carries additional load until crushing or buckling or reinforcement fracture occurs. Okay, so this is additional path here. Localized crack become wider, reinforcement shows significant hardening, and compressive damage appears. Um, and although fiber reinforcement is able to helps the restrain the spalling. These two paths highlight how the tensile and compression resistance of HPFRCC changes beam behavior compared to conventional concrete based on these two observations. Um, so so that is how it is very different. On the other hand, the next part of the this slide, which shows behavior or damage in plastic hinge of cantilever columns subjected to cyclic load. Okay, so here the research showed that there was significant difference in damage pattern in the plastic hinge region without and the HPFRCC showing no signs of spalling, whereas concrete specimen we can see significant spalling with large crack patterns. Now, what this large crack pattern done is that is basically in HPFRCC we can see that there was excuse me. So we can see that a behavior of plastic region in reinforced HPFRCC components uh, has longer, much higher number of cracks, whereas the reinforcement is also exposed here. So that leads to higher accumulation of plastic strains, and buckling of reinforcement is also seen here. So because of its fiber bridging capacities, UHPCs or HPFRCCs or even ECCs, which have higher ductility, strain ductility capacity, they are able to undergo higher drifts in cyclic loading and provide a much fuller hysteresis curves. So this is another test here. We look at how these beams behave differently. Now, if we focus on cracking behavior in a reinforced concrete beam at large drifts, what we usually see is just few wide cracks, often accompanied by spalling of concrete cover, which can be seen here in the cartoon B. Okay, once that cover is lost, reinforcement becomes exposed and less stable. Now compare that to reinforced HPFRCC beams with the same reinforcement ratio. Instead of just a few cracks, we see a network of many cracks, which was also visible in the previous slide. These are kept narrow because fiber bridge across them, and which not only prevents the spalling but also provides lateral restraint to reinforcing bar, so that way the bars are not buckling. And we can also talk about what happens under large displacement reversal. In HPFRCC, localized cracks can sometimes fully connect across the beams, and when that happens, then shear sliding can occur along that crack plane. So imagine if cracks are reaching from one end to other end, then basically we can see that at that location it is very weak in shear, and we can see some shear occurring at that location and in the reinforcement as well. So now, if we look at the hysteretic behavior, which is also shown in the next slide here. So now if we focus on the hysteretic behavior, in conventional concrete, hysteresis loops are often, pinch inwards as the load reverses. This pinching effect reflects low stiffness during the tension compression transition. It happens because the wide cracks lead to bond deterioration and reinforcement slips. So there is, the erosion of the bond. So the structure loses stiffness and energy dissipation capacity. Reinforced UHPC or FRCC, HPFRCC by contrast show much less pinching. That's because the bond between the reinforcement and the matrix is preserved by these fine distributed cracks and the fiber bridging. As a result, HPFRCC beams can dissipate significantly more energy during an cyclic load event. So this is what I was talking about. You see, these curves are more fuller, but if you have seen conventional concrete under cyclic loading, so after it reaches peak, or basically once the load cycle reverses, we would have seen not a steep or not a straight increase in the load, but it kind of goes this way before it kind of picks up on the load. So there is some initial displacement, which is basically equivalent to closing of those wide cracks that happens in normal concrete. So that here is not seen, and that's why we get more fuller curves, and the energy dissipation is equal to area under these hysteretic loops. So the larger the area, more energy is dissipated, and that's why these are able to dissipate higher energy events as well. So as we talked about that, there is, inherently a stronger bond between steel and concrete due to the high strength concrete. This stronger bonding comes from HPFRCC's ability to restrain splitting cracks as well. In other words, when the matrix grips the steel bar more tightly, resisting the crack propagation around the reinforcement, while this is generally beneficial for the load transfer and bond strength, it also means that a localized cracks, when it is formed, the plastic deformation of the reinforcement gets confined to very short region near to that crack. As a result, the strain in the steel accumulates quickly in that small zone. This localized concentration of plasticity leads to sharper curvature, faster strain accumulation, and ultimately, possibly, early bar fracture as well. Okay. So Sorry about that. All right. So now, beam that fails after crack localization are particularly vulnerable to this effect, which I was talking about, that reduced ductility and fracture of localization of plastic strain in reinforcement. Once first crack localizes and fiber bridging begins to degrade, the beam's load capacity often drops. This reduction prevents the formation of additional localized cracks. In such case, we usually see only one or two localized cracks, and because reinforcement is forced to deform around them, the plasticity concentration accelerates the steel failure. This is one reason why beams failing after crack localization exhibit lower ductility, which can be seen in the first plot here. That is the effect of lower reinforcement as well. On the other hand, in the beams that fail after gradual strain hardening, and strain hardening can occur in beams on account of higher reinforcement, as well as ratio between what is the tensile strength and comparison to that with the reinforcement provided. So here the hardened reinforcement carries greater flexural tension force than it did um, at the point of initial crack localization. This added capacity allows new localized cracks to develop, which distributes the reinforcement plasticity over larger portion of the beam instead of all the deformation happening in a small zone. The plastic strain spread out over the beam length, and this results in member ductility. An important trend here is that ductility improves with higher reinforcement ratios. Under both monotonic and cyclic loading. Increasing the steel ratio kind of helps the rate at which the load capacity drops after the crack localization. It also encourages development of multiple localized cracks. Interestingly, a similar effect can also be achieved by not adding reinforcement, but reducing fiber volume, not to zero, but maybe lower than 2%. By lowering the fiber content, the tensile strength of the matrix is slightly reduced. This reduction makes it easier to form multiple localized cracking instead of concentrating damage at one or two location. As a result, steel plasticity gets distributed over more cracks, which increases drift capacity and delays the reinforcement fracture. Now we look at this basically shows us how different how different the behavior of UHPC and conventional concrete depending upon fiber ratios and reinforcement ratios can be. So what this shows is there is a distinct behavior difference in the plasticity zone, and therefore it is important to capture that. How we capture this behavior analytically. So this plot basically shows comparison of ultimate rotation computed from simulation versus analytical formulation of plastic hinge length. So the plot A is basically what it shows is the simulated rotation versus as the rotation calculated by Paul and Presley, who have come up with analytical model for conventional concrete. So ideally, if the model matches the simulation, the plot should have a fit which is 45 degrees, such as shown in the plot B here. That means these models are not good enough to, or they do not capture the plastic behavior or the capacity of materials like UHPC. So basically what is showing here is, and what's fascinating to note is that when we compare the numerically simulated plastic hinge lengths with existing empirical equations, we find significantly high discrepancy, and the simulations consistently predict hinge lengths about 0.25D to 0.75D, which are shorter than those given by existing equations. So this difference is not surprising when we consider the background of empirical equation, as I said. Those were developed using conventional reinforcement data, which does not account for the issues we just discussed, namely crack localization, strain concentration, multiple cracking, and other things. So as a result, if we directly apply those existing equations to reinforce HPFRCC members, we risk over predicting the plastic rotation and ultimate rotation capacity. That means our analytical model would suggest these members can deform more than they actually can, which can be unconservative in seismic design. And in the next section, I'll talk about analytical models and how we usually develop them. So basically we are talking about the challenges here. So there are talking of challenges, what I want to talk is that there are limited existing experience in UHPC. It's a still relatively new material in structural applications, and the number of full-scale cyclic testing or system-level evaluation is very small compared to traditional concrete. This makes it difficult to validate numerical models with sufficient confidence. Second, there is a issue of time and resource needed to create a larger experimental database. Full structural testing, especially such as under cycling and seismic loading, is extremely costly and labor intensive. So unlike conventional concrete, where smaller scale data can often be scaled up, UHPC are highly sensitive to details like fiber orientation, casting method, mixed design, such things. That means we cannot always extrapolate, and instead we need more dedicated case specific studies. Third is we face challenge of rapidly changing material properties as well. So UHPC is not one static material. It's a class of UHPC is basically a class of materials, and it's continuously evolving with new fiber types, fiber dosages, variation in mixed formulations, also new kind of supplementary cementitious materials. So these are constantly introduced. So this makes it very difficult to create a single standardized model, because by the time the model is validated, the material itself might have advanced further. So in short, modeling process for UHPC is not just about refining numerical tools, it's also almost keeping up with a moving target. So limited experiments, the time required to scale up the database, and rapid pace of material innovation, um, uh, you know, are basically we are chasing behind the material progress. And that is why developing robust, adaptable models. So adaptable is the keyword here for UHPC remains one of the larger challenges on how we want to simulate this behavior and predicts its performance under seismic loading. So in summary, we discussed advances in guidelines for structural engineering, structural design in UHPC. We looked at an example of how to plot um, a moment curvature, and then basically how to use that moment curvature to define the factored resistance. Uh, we also saw that UHPC, as you know, as it might appear because of its fibers and steel fibers and its ductility, it appears that it will always give a ductile behavior, but it's not true. They have unique failure modes, and we need to understand this better, that what is the relation between the reinforcement provided and the tensile capacity of the UHPC. And based on that model, we need to come up with what would be the predicted failure path. And it therefore necessitates a new need for models in seismic analysis. All in all, though, as we looked at the potential of this material is, definitely proven. It has significant potential to improve life and safety and reduce damage through these materials when properly engineered and utilized in areas especially prone to seismic events. And otherwise as well, these materials are owing to their high strength mechanism and also tensile strength, they are able to undergo higher drifts and larger hysteresis loop under seismic loading, apart from coming up with neat solutions for buildings and bridges. So with that, I conclude my presentation. I think we almost have 15 minutes less left for questions and answer. I had to rush through last few slides because I was trying to at least have 15 minutes for any questions and answers. And I understand that this is, towards the end of the day for you guys. So, thank you for maintaining interest in this presentation. I tried to capture a lot. It was very dense. We talked about mixed design. We talked about how those mixed design can convert into compression and tensile behavior properties, mechanical properties, how those mechanical properties are evaluated and got into the design models for flexure and shear. And then basically we took it further that what is the post-peak behavior which we tried to capture into seismic design. So it must have been very dense, and I apologize if a lot of things were left in clear. It was too much material to probably pack into some small time. But I again thank you for everyone maintaining their patience and interest in this topic, and also providing me an opportunity to bring forth these interesting new guidelines and interesting new research in the field of UHPC. With that, I conclude. Thank you very much.
Well, thank you so much. So we have a few questions in our chat box. Would you like me to read those for you?
Yeah, I'll try to open the chat box, but if you want to read, that's fine.
Okay, so first one's from Arsalan Khan. He asks, which software or method did you use to capture appearance of cracks on beam with loading?
So do you mean that the video? I think
Sir, if I can speak.
Yeah, go ahead.
Yes, a very nice presentation and very relevant topic, by the way. I actually wanted to ask you in the somewhere in the beginning of your presentation, you showed us an image of a loaded beam. The beam was being loaded and the cracks were propagating.
Yeah,
And
yeah,
there
yeah.
was purple
So this one?
background. Yes, yes, it was a camera technique, some software. I wanted to ask, it was really brilliant idea. So I wanted to ask which method was it?
Yeah,
Great,
so so this is a digital image correlation. So there are number of softwares which can be used for digital image correlation. What it does is that so if you can see this beam, that beam, if you see those randomly speckled black and white spots, those are not the aggregate, but the beam is basically painted on painted white, so that gives a white background, and on that you can randomly speckle some black paint dots, and they have to be random. So what after that we load the beam, put a camera, and then capture sequence of images at every second. Okay, and these are fairly slowly loaded beams. So we can, I think, one image per 5 seconds or one image per second is also enough. Once those images are captured, uh, because they are captured from a stationary point, and they have these speckles which are moving. So the software which comes with digital image correlation, I think you can, if you search, you will get a number of softwares for digital image correlation. So you provide those bunch of images, which could be 1,000, 5,000 images, and then it will create a based on those speckles and movement of the speckles, it will create a vector field, a displacement vector field, and that vector field are processed, and you can calculate strain, displacement vectors, and everything, and those are also plotted very nicely. So so look up digital image correlation, and this is used not only in I can say low loading rates, but they are also used at high strain loadings. The only thing is that there you require a camera which has very high frames per second rate. So so that was it.
Thank you, sir. That's great. Thank you. I will have a look at it. Thank you very much.
All right. Thank you for the question.
Well, we have another question from Sandeep. Uh, for any alternative method can we use instead of SHM? SHM is commonly used but not up to mark and very expensive.
Can you tell me what is SHM? I might be missing the acronym here.
It is structure health monitoring.
Oh, okay. So structural health monitoring is a very excuse me, for particularly for UHPC. Is the question what kind of SHM can we use for UHPC particularly?
So the question itself seems a little incomplete. Mr. Sandeep, you were there in the meeting. Yeah, if you can ask. Or maybe you can clarify it. Yeah.
No, so I think this is a fairly new materials in the sense of in the field of structural health monitoring. I think uh, people have tried to capture I would say there are ongoing tests which are trying to capture fatigue behavior and how those health monitoring systems for fatigue behavior can be utilized for actual structures. So that is I think an area in UHPC that is still being investigated particularly. It's, as I said, it's a fairly new material. The guidelines have just come, at least in the US for structural design, have been released only last year, and those two focus just on the structural um design for loads. In India, such as we have IS 456 and another code for a detail of concrete structure under seismic load or seismic detailing. There are no codes which define about long term health behavior. So since there are no lack of insights regarding how a very long-term behavior and what kind of monitoring would we require. So I think that question is up for investigation, and I'm sure researchers must be working on developing tools and mechanisms for structural health monitoring which are cost beneficial in the field of UHPC.
All right, sir. So with this, we would like to conclude our session today. We have had a very engaging session and insightful one. Thank you so much for accepting our invitation. Swatambara ma'am, would you like to say something?
So thank you, sir, for gracing and accepting our invitation today. And the session was very insightful and lot of information you have given to the participants. I hope the participants would be definitely going to be benefited out of it. So thank you so much once again. I would
All right.
request Jay to please take a group photo so that we can have a record for today's.
Mr. Rishikesh, if you would want to address you,
Thank you,
probably.
Ketan. Thank you, Ketan, for joining us today. The presentation
course.
was really nice. I
Thank
think
you.
a lot of information about what goes on in the US. I mean, people in India can also come to know about it now.
Yeah, I know that there is a guideline, probably as it's not as detailed, but there is a definitely guideline. I was researching this and I looked up that there is a not a guideline, but at least a report published by Ministry of Road Transport on the use of UHPC. And one thing that I would say is that based on my interaction with industry, I have seen that UHPC is more uh, aggressively used in India as opposed to US. There are more number of projects and people have seen a lot of benefits in this material, and there is new bridges and even the ministry itself propagating this material fiber reinforced concrete or UHPC, that adds to people adopting it more quickly. However, I think all over the world, the design guidelines are, as I mentioned in my last slide, the design guidelines are kind of lagging behind the material development as well. It's always catching up with what material development is going on. So it was an interesting opportunity for me to present, and I really thank you guys for giving this opportunity for me to present this topic. And thank you everyone. Namaskar.
Yeah. Thank you. I think we can end the session now.
All right. Thank you.
Yeah.
Good
We
evening,
can-
everyone.
Yeah.
Good night.
Good night.
Can
Good
have
night.
Yeah.
Yeah, the picture have been clicked, ma'am.
Okay. Okay. Thanks.
Thank
Thank you, everyone.